Hello everyone, my name is Naje George and I will be presenting to you the propagation of ab-initio quantum dynamics. And so to give a little background, my research will be focusing on non-adiabatic molecular dynamics, which are simulations that provide some sort of observable like fluorescence intensities, without needing prior knowledge of the system or mechanisms. And what I mean by this is that, take for example this molecule that I have over here that has 50 plus atoms, is that we don't need specifics such as a reaction coordinate or where it is on a reaction pathway. We just need an initial state so that we can propagate on it. And this is very useful for fields in spectroscopy and photochemistry. Within non-adiabatic molecular dynamics, we will be focusing on the method of Tully's fewest switches surface hopping, which are used primarily because in non-adiabatic molecular dynamic simulations, we typically have to propagate both the nuclear wave functions and the electronic wave functions. But with this method, we don't need explicit propagation of nuclear wave functions. We can just propagate the electronic, which reduces computational costs. Um, some of the current methods of propagation, however, have problems with accuracy and stability, in which accuracy is very limited by the size of our time step. We can only have really small time steps and can propagate only for small periods of time. And stability is often conditional, and after the set period of time of stability, schemes will often blow up or just become massively unstable. And so going into the molecular Schrodinger equation, which is the main meat and potatoes of what we're doing here, or what we're looking at, the time-dependent electronic Schrodinger equation is defined as um, the partial derivative of a wave function being similar or being equal to the Hamiltonian being applied to that wave function. The Hamiltonian being composed of the kinetic energy and potential energies of these different interactions, electron-electron, electron-nucleus, nucleus-nucleus, for example, and with r, which is our spatial coordinate, being our nuclear trajectories. Um, we can expand this electronic wave function into the Bohr-Oppenheimer basis, and then when putting this expansion into electronic Schrodinger equation, we get a matrix discretization of an operator being applied to an amplitude vector or a wave function in order to get future states of that wave function. And so this goes right into our formal solution, which we can describe as a unitary propagator being applied to our wave function. And one of the main things to consider is that this unitarity must be conserved, because if it's not, then errors can easily prop up and be accumulated throughout our propagation. And so we approximate this unitary propagator with a Magnus expansion and a 2-point Gaussian Chebyshev to get a fourth order approximation that we believe will approximate this unitary propagator actively, limiting those errors, um, while also not being computationally expensive. Um, Another thing to note is that throughout our propagation, not only must unitarity be conserved, but energy and wave function norms must be conserved too. Um, we pick these main three properties as well as some symmetries, because this will give us these three properties give us the most information about our wave function, and specifically energy and wave function norms tell us how the behavior of our particle. Um, Getting to surface hopping, which is the main feature of Tully's method, this is the act of switching from one Born-Oppenheimer state to another, often lower Born-Oppenheimer state. We do this by comparing a random number against a transition probability that is computed based on our Hamiltonian at every time step. One key thing to note is that this causes a discontinuity in our potential energy, but our total energy, wave function norms, and unitarity must still be conserved during the surface hop. We do this we adhere to this by rescaling our velocities along the direction of our non-adiabatic coupling vector. And you can see this in the equation shown here. By rescaling our velocities, we also correct our momentum and kinetic energy to account for the change in potential energy that happens. Okay, this leads us into getting a closer look at our errors. Um, This was run on a formaldehyde molecule, one which you saw on the first slide, 1 carbon, 1 nitrogen, 4 hydrogens. And we can see that when we ran a suite of 30 trajectories and averaged the total energy of all those trajectories, we see a general decline in the total energy, which shouldn't happen if energy is being conserved. And looking closer at our separate trajectories that are contributing to this average, we see that some of them have a discontinuity once the surface hop occurs, which once again shouldn't happen if we want energy to be conserved. So we suspect that this decrease in energy is caused by the discontinuous energy that we see in our individual trajectories, as well as the lack of unitarity in our propagation accumulating errors at every time step. If you want to know more, please come to my poster. Thank you.